Okay, good day, everyone. We will get started before any questions before we get started. All right, I guess we continue where we left off from last class, and we're gonna finish off all the sessions today, and we can move on to the final review next on Friday. Okay. So next Wednesday you are taking the final exam. So let's take a look at the section 4.4 on accounting. Okay. Let's talk about some of the accounting rules. Okay. All right, so accounting basically it's like fundamental rules, used to calculate some of the probabilities. So now we're going to take a look at it, right? So in many probability problems, the biggest problem is finding total number of outcomes. So finding all the outcomes it's challenging for a lot of like different problems. And for example, let me just give you a very simple example. If you roll a die. Roll the dice 10 times. And it will be extremely difficult, right, to list all the possible outcomes.
You're not showing anything.
Yeah, I see. We got to share that. Okay, here you go. So we on chapter 4 on accounting, right? I just present you an interesting issues on the probability, which is throwing dice. Throw dice like 10 times, right? Then it would be extremely difficult to find out all these possible outcomes. Okay, make sure I share the screen properly one more time. Okay, so all the possible outcomes, it's almost like impossible to list it. So that's what we mean by this finding all the outcomes. It becomes a very challenging task, right, in probability. And all we can do is try our best to find the best possible outcomes. Okay. Now let's look at the fundamental counting rules. So for a sequence of two events in which first event could occur in m different ways, the second event occurs in n different ways, the events together could occur in m times n ways. Remember, for the multiple choice questions from the multiplication rule, multiple choice questions, right? Let's say we have two questions, right? With two questions with 5 answer choices. And we could apply the fundamental counting rules, assuming those two questions are not related to each other. I mean, they are independent. So for the first question, you have 5 possible answer choices. Second question, you have 5 possible answer choices. So if you look at 5 times 5, that gives us 25 possible answer choices, right? You can also use a tree diagram to come up with all 25 possible outcomes here. But that's just, so it's kind of convenient to use the fundamental counting rules to get all these possible, to get the overall possible outcomes here, which is 25. Okay, and just very simple example, right, to elaborate on this. And next thing is the factorials. So factorial using this symbol, right, explanation symbol, and typically we just look at a factorial as a product of decreasing positive whole numbers. So 4 factorial start with 4, then you multiply by 3, by 2, by 1, we end a number at 1. Okay, so that's why we get 24. 4 times 3 times 2 times 1 give us 24. Similar idea, right? What will be the 5 factorial? You start with the 5, right? Decrease by 1, decrease by 1, decrease by 1, decrease by 1. Until you get to 1. The last number is always going to be 1. And that's going to be 5 times 24, right? 4 times 3 times 2 times 1. We already know that it's 24. So it's 5 times 24. That's 120. Okay. So this is where the factorial comes from. And two special things about factorial. 0 factorial is 1, right? 1 factorial is also 1. Those are specials. So anytime you see 0 factorial, it automatically becomes 1. Now let's think of how do we list n factorial. We do not have a concrete number now. What if it's just a variable n? So you start with the n, right? Then reduce by 1, minus 1, right? And reduce by another 1, minus 1 becomes minus 2, right? Reduce by 1 again, reduce by 1. Eventually, the last 3 numbers will be 3 times 2 times 1. It ends with 1. Start with n, ends with 1, right? No matter how complicated that is, it's always the case. Okay. So that's factorial. Any question about factorials? Let's think about this, right? What will be the 5 factorial dividing by 4 factorial? We know 5 factorial is 5 times 4 times 3 times 2 times 1. Okay. Multiply 5 all the way to 1. 4 factorial is 4 times 3 times 2 times 1. Notice that we do have the exact same numbers that get canceled. So 5 factorial over 4 factorial is exactly 5. Okay. So that's kind of interesting phenomenon when we divide into factorials is we always going to cancel some numbers. Okay. All right. So let's take a look at a number of different permutations of n different items could be arranged when all n of them are selected. So factorial rules reflect the first item may be selected in n different ways, second items may be selected in n minus ways, and so on. Think about this. Let's say we have 5 students. We are sitting 5 students in 5 chairs. Okay, so think how would you do that? We have 5 students lining up outside of the classroom, and here we have 5 chairs. Okay, first chair, second chair, third chair, fourth chair, and the 5th chair. So for the first chair, we have 5 students outside, right? So basically we have 5 options. So this is 5. We have 5 students available to sit in the first chair. Now, once one of the students sit down, now we only have 4 students left. So by the time we get to the second chair, only 4 choices available. Third chairs, 2 students sit down. We only have 3 options, 3 students available, right? To sit on the third chair. Same thing for the 4th chair, only 2 students remains, 2 options available. By the time we get to the 5th chair, only 1 student left. Okay, so sitting 5 students in 5 chairs will be 5 factorials. Okay, so same thing like if you have n students sitting n students in n chairs. Same idea, right? That would be n factorials. That's exactly what this factorial rules is stating. You can simply use a very simple example like 5 students, keep it small, and then you can increase the number to a variable number, right? So it could be n chairs, n students in n chairs, that becomes n factorial. But the rational is it's same thing, right? For the first chair, you always have, in this case, 5 students, you have 5 options. N students, you have n options. By the time you get to second chair, you have 1 less option, right? So it's -1. Third chair, -2. Fourth chair, -3. Okay. And then eventually we get down to the last one, right? The last chair with 1 student left. Okay. So that's basically the factorial rules. And the factorial rules is foundation for permutation combinations. Right? Think about the permutation rules, right? Now, assuming all items are different. Now, for like students, they are different, right? Let's say you have 100 students, they're all different. So requirements, there are n different items available. Okay. And then we select R of the n items without replacement. So this is important. You pick an item, you assign the position, then the item is not available anymore. So it's gone. So, and then also we consider arrangement of the same item to be different sequence. Permutation of ABC is different from CBA. So it's counted separately. So meaning we do a rearrange those items when we put them in the sequential orders. So here, put into a simple language is pick items out of a total of n items. And then the order matters. Meaning order of the rearrange those items matters, order matters. And that will be the essence of the permutation. Okay. And the permutation rule is n factorial over n minus r factorial. So it's using NPR, right? Permutation is denoted by NPR. So it's equal to n factorial, total amount of items there, factorial over n minus r factorial. Okay. Remember, we do rearrange those r items when we pick them out of the n items. Okay. So think about this, right? Let's say we have 3 letters, A, B, and C. How many ways we could rearrange these 3 letters? Okay. Think about this. Right? So you have 3 different spots for these 3 letters. For the first spot, first, second one, third one. For the first spot, we have 3 letters available. By the time we get to the second spot, only 2 letters available, since we already placed one of them. By the time we get to the third spot, only 1 item is available. So it's 3 times 2 times 1, 6. And you can list it, right? It could be A, B, and C, right? It could be AC or AC and B. It could be BCA, BAC. Could be CAB, CBA. Okay. So that's why it's a 6 different arrangement. That's what we mean by, let's say you pick 3 items, 3 letters out of 26 letters, right? Alphabetical letters, and order matters here, right? So meaning we do rearrange those 3 letters afterwards. And we have 6 different ways to rearrange those 3 letters. And that's basically just to give you some idea how this permutation works. And the assumption is all items are different, right? 26 letters, they're all different. Okay. All right, any question about the permutations? It's built based on the factorials. All right. And when some items are identical to others, then we use different n items available, and some items are identical to others. We select all of n items without replacement. We consider rearrangements of this distinctive item to be different sequence. Then the permutation will becomes n factorial over n1 factorial. So we have n1 alike, n2 alike, n2 identical items, nk identical items. So it's n factorial over n1 factorial times n2 factorial all the way to nk factorial. So this is just when we have some identical items, right? Let's use a different formula for permutation. But we barely use this one. Just want to bring this to your attention if you have identical items. And now the combination rules. Okay, so basically combination works like this. You pick R items out of a total of n items. And the order does not matter, meaning when you pick those R items, you do not rearrange them. Order does not matter. Order of the rearrangement of those R items does not matter. As you can see, the difference between combination, permutation is R factorial here. Meaning for combination, we have less outcomes because we do not rearrange those R items. So that's why we divide by R factorial here. So we have n different items available, select R of them, R amount of them out of n total items without replacement. And order does not matter, meaning rearrangement of the same item to be the same. ABC is equivalent to CBA, right? No difference. So here it will be, yeah, with a lot less choices, right? In terms of combination. And combination, permutation, they are closely related to each other. Right? Permutation just has more outcomes, that's all. How many more outcomes? R factorial times more outcomes for permutation. Because for permutation, we need to rearrange those R items. That's why we multiply by R factorial for the permutation. Okay. So any question on combinations? Now let's look at how we apply this, right? Permutation versus combinations. The only thing is ordering of the same items to be counted separately. If it's counted separately, that's permutation. If we do not count it separately, then it's combination. Okay, so it's a distinguishment whether or not we rearrange those R items afterwards. That matters, right? That gives us two different approach, two different route to go. Okay, think about this. So let's say a byte is a sequence of A numbers, or either 0 or 1. And then our computer system, right? Internet, computer system is built based on byte. Okay, so it's remember when they first programmed the computer, they use 0, 1, right? For each command, for each command for the previous step. So 0, 1 is so basically you have A numbers here. So they want you to find out what will be the possible bytes here. How many possible bytes available? 3, 4, 5, 6, 7, 8. So this is first, second, right? Second byte, third byte, fourth, fifth, sixth, seventh, and eighth. For the first byte, either 0 or 1, right? You have two numbers available. So you have two options. By the time you get to the second byte, two numbers available. Third byte, two numbers available. Fourth, same thing, right? That does not change. So since they are all independent, you multiply across. This turned out to be 2 to the 8th power. And 2 to the 8th power should be, I think 200, let me see. 2 to the 8th, it's 256. 256 bytes, total bytes. And that's how you handle this type of problem using the counting rules, right? And here, typically, if it's binary, this is what we call binary outcomes. If the outcome binary, for example, like flip a coin 8 times, right? We know that the outcomes are either head or tail, so it's binary outcome. Right? It's head or tail. Then the total outcomes will be 2 to the 8th power. Okay, so 2 to the 8th. Same thing outcome, so 256 outcomes. All right. Let's say you check 8 newborn babies. Then same thing, the babies are, the gender of the baby are binary, right? Either a boy or girl. So since this is binary outcomes, so we're gonna get a 2 to the 8th power, meaning we're gonna have 256 outcomes. So basically they are equivalent, right? So the computer system, was invented based on the people understanding of probability from the real life, like newborn babies, flip a coin, and they just build based on this concept, right? So they are interconnected in some way. All right, now think about this. Let's say we have a history pop quiz. A student to arrange the following presidents in chronological orders: Hayes, Taft, Polk, Taylor, Grant, and Pierce. Right, we have 6 presidents, right, in history. If an unprepared student totally guess, what is probability of guessing correctly? So you want to put into the proper order, right? And then you want to ask students, what will be the chances? What's the probability of guessing it correctly? So you want to look at all possible outcomes here. If somebody did not prepare at all, right? We'll randomly select first president, second president, third one, fourth one, fifth one, and 6th one. Okay. So let's say just randomly guessing for the first spot, we have 6 presidents available, right? So 6 options available. And since we pick one already, by the time we get to the second one, only 5 presidents remain, 5 options available. Same thing by the time we get to the third one, 4 options available. Fourth one, 3 options available. Fifth one, 2 options. The last one, by the time we get to the last one, only 1 option is available. So this is exactly what we call the factorial, right? 6 factorial. And 6 factorial is 720, right? The 24 times 5 times 6, 720. Okay. All right, any question on this? Just like arranging 6 students in 6 chairs, right? Very similar idea. Okay. Same thing here, just guessing them randomly. You have 720 different outcomes. However, only one of them is a proper outcome, right? So the probability of guessing that correctly is 1 correct outcome out of 720. If you look at the actual probability, it's going to be, it's pretty low actually. That means this is approximately equal to 0.0013888, right? Meaning the chances of guessing this correctly in a row is less than 1%, right? It's 0.14%, which is extremely low. If you just, so that's why never, multiple choice questions never easier, because if you do not study, just guess it, and the chances of getting correct answer is very low, right? Because of, based on this probability calculation, you understand why that happens. Okay. So this is the probability of guessing correctly, 1/720. All right, now let's take a look at this. In the Pennsylvania Match 6 lottery, winning the jackpot requires you select 6 different numbers from 1 to 49. Okay, so pick 6 numbers out of 49 numbers, right? 1 to 49. Here we have 49 numbers. How do we know it's 49? You do 49 minus 1, adding 1. Adding 1 meaning including the first one. So we have 49 total numbers. Now, the winning number may be drawn in any order, meaning order does not matter, right? For those winning numbers, think about this. Anytime you play the lottery game, as soon as you have the number, you pick the number, no matter what order you put a number, as soon as those number matches with the winning number, you win the game. So here, order does not matter. All right, so now let's rephrase this, right? So you pick 6 different numbers from a total of 49 numbers. And order does not matter. As soon as you have all the winning numbers, all 6 of them, you win the game. And order does not matter. What does this become? Any suggestion? Six different numbers out of 49 numbers, order does not matter. So this is exactly the combination, right? NCR, right? So it's going to be 49C6. And if you apply the formula, if it is NCR, will be n factorial over r factorial or n minus r factorial times r factorial. So basically here we're going to have n is 49, so 49 factorial by 49 minus 6 factorial times 6 factorial. And let's look at it. So 49 times 48 times 47 times 46 times 45 times 44, 43, all the way to 1. Okay. If you look at this one, this is 43 factorial. Start with 43 all the way to 1. Okay. This one is 43 factorial. We don't have a 6 factorial. Okay, so 6 times 5 times 4 times 3 times 2 times 1. And notice that everything out of 43 will be canceled. It's the same number. That's why when we divide 2 factorial, we can always cancel some numbers. So basically just 49 times 48 times 47 times 46 times 45 times 44 dividing by 6 factorial on the bottom. And I can show you how to get this done in Excel really quickly. Maybe let me just put into the calculator, get the result first. 49 times 48, 46 times 45 times 44, multiplied by 43, and dividing by 6 factorial. And that turned out to be a huge number, actually. It's 60,130,408. Okay. So basically you have 601,304,088 possible choices, okay, available here. And we know that only one ticket is winning number, right? So the probability of winning, it's 1 over that. 601,304,088. And if you look at the probability of that, it's extremely low. this is almost like impossible. That's why sometimes you probably hear that nobody win a lottery game for a while, just because the chance is so low, right? This is the chance we're looking at in terms of winning this pick 6 lottery game in Pennsylvania. Okay. Any question on this? Also, I'm going to show you how to do this really quickly in Excel. All right, let me share the screen with you. All right, we can get it done very easily in Excel. Okay. Let me just open a new sheet. And in terms of calculating combination or permutation, right? Combination. Okay, combination, you do COMBIN, right? So putting combinations, the number of total numbers is, in this case, is we have 49 numbers available. I'm picking 6 out of 49. And order does not matter, right? So we get that. Here we go. Why okay, I guess the calculation in the PowerPoint is not right. So this is off. I probably didn't put in the right order. The correct answer should be that one. Okay, so I need to modify this. Okay, go back. This is right input, right? Combination, total numbers, and 6. Okay, then we should get this. So it's 138. Okay. So it's 13,983,816. Okay. Go back here. We need to modify this. So this is not right. Okay. This is not right. Should be the one we just see. 13,983,860. 983,816. Okay, so that would be 1 over this. So this is all total of 13,983,860. And divide that 1 by share this. So this should be 1 over 13,983,860. All right, so this turned out to be still in a very tiny little number, so 0.00000072. Okay, still right with the probability is kind of almost like impossible. Right, it's almost like it doesn't work. Okay, so this is off. Okay, but yeah, always you can always double check with Excel, right? If you do it by hand and then the number turn out to be off, right? So you can check using Excel to do it. It's much quicker and easier to use Excel to calculate this. So this is combination. What if it's a permutation? You can also calculate permutation with the same condition, right? Permutation now with the 49 numbers, right? Picking 6 out of 49 numbers. And we do rearrange those 6 numbers. And if you look at it, it will be a lot more, right? How many times more we can divide them, right? So divide this by this. You get 726 factorials. We look at factorial. You can also calculate factorial by typing FACT, putting 6. 6 factorial is 720. Meaning here we rearrange those 6 numbers we picked, right? And the outcome is a lot more. Okay. All right, so that's that's difference between the combination, permutation, and using Excel, you can get it done really quickly. Right? Type in the right formula, and you get a result. All right, and that's pretty much everything on this. Maybe let me just give you an example. Let's say and you can practice on it, right? So let me give you an example now. So you can look at this new example. Okay. Slide. So now think about this. Text box. So let's say in a corporation, 12 board members, right? So on the board, any corporation have a board, right? They have 12 board members. So they are voting on those important issues for the company, for the corporation. So now part A, you want to select. So if we want to select 4 board members, and form ethics committee. How many possible choices are there? Now versus part B, right? We're gonna come up with the part B. So part B, if we wanna select 3 board members, sign each member with the title. So the title will be President, Vice President, VP, and Secretary. So those are the 3 titles they're gonna each one gonna have. So how many possible choices are there? Okay. Yeah, so I'm gonna give you 5 minutes. You guys can work on this, see if you understand how to solve the problem using the combination and permutation. Okay, so let's look at the solution for this. So for part A, it should be a combination, right? Because we're picking, okay. So pick 4 items. Okay, share the screen. So it doesn't allow me to write. Let me just try to fix it. Okay. This. Okay. Here we go. So you're picking 4 board members out of total 12, right? So picking 4 board members out of 12. And since it's an epic committee, so they all become committee members. So there's no titles involved here. So the order does not matter. So the order does not matter. So that's typical. That's a typical combination. Order does not matter. So it's a combination. So we just apply the combination formula NCR, right? It's n factorial over n minus r factorial, r factorial. So pi will be n here will be 12, 12C4. So that becomes 12 factorial over 12 minus 4 factorial, 4 factorial. And we can expand it. So 12 is 12 times 11. And we know a factorial, this is a factorial, a times 7. And we also have 4 factorial, so 4 times 3 times 2 times 1. Okay. And we know everything after 8 get cancelled. They are the same. And then we get a 4 goes into 12 3 times. 3 get cancelled. 2 go into 10 5 times. So basically, we're just multiplying 11 times 5 times 9. Okay, that's all remains. And let's see what that is. 55 times 9. It's 495. Okay. Yeah. That should be it. So we're just simply using the calculation to get the result. Now let's double check that in Excel, right? Quickly check that. So using combination we have total of 12 numbers, picking 4. Okay, 495, right? So that should be good. Yeah. So total 12 numbers, picking 4 out of it. It's a combination that turned out to be 495. And let's go back really quickly. Yeah, so second part is you're picking 3 board members, right? But each one of them gonna get a title, right? So that means order matters, right? Because let's say you pick Harry from 12 board members. Harry could be the president, could be the vice president, could be the secretary. That's different outcomes. So here, order matters. So that means it's permutation. And we're going to use permutation to handle this. So it's NPR will be n factorial over n minus r factorial. That's the formula for the permutation. That will be 12P3. That means it will be 12 factorial over 12 minus 3 factorial. Okay, and this turned out to be 12 factorial over 9 factorial So that's 12 times 11. Same thing, right? Everything 9 all the way to 1. Okay. And then 9 factorial on the bottom is 9 times 8, right? All the way to 1. And we know everything after 9 will be canceled. Okay. So basically just multiplying 12 times 11 times 10. And this turned out to be 1320. Okay, and we can double check that quickly in Excel. So this is permutation PEI mu T. And we're putting 12 and picking 3. Right. Picking 3 members out of 12 other matters. Yeah. So 1320. Go. Yep, so we double check the answer in Excel. They both good. And that's how you distinguish the permutation combination. And this is also very useful knowledge to have in terms of handle the real life problems. Okay. And this is pretty much everything on the section about accounting rules. And also the last section we're gonna go over is the Bayes theorem. And then also I'm gonna mention the homework assignment one more time once we finish lecturing. Okay, so now let's open the PowerPoint for section 4.5. Again, the section here does not align with the textbook, right? I'm using different publishers' textbook for this. So the PowerPoint does not, it's not, the contents are consistent, but the section number may be slightly off. Okay. So this is the last topic, it's called Bayes theorem. And Bayes theorem is an application of the conditional probability. If anybody asks you what is Bayes theorem, it's an application of the conditional probability. Remember, we talk about conditional probability. It's probability of A given that event B occurs, right? Probability of event A given that.
Professor, I can't see anything.
And I forgot to share. Okay. How about now?
Yes, it's fine.
Okay, good. Thanks for the reminder. All right. Again, Bayes theorem is an application of conditional probability, and we do write a conditional probability as this, right? Probability of event B, event A. Let me just quickly remind you what the conditional probability is. Probability of event A given that event B occurs, right? So this is interpretation of this is probability of event A given that event B occurs and it has impact on event A. Event B occurs. The impact on event A. So this is the meaning of the conditional probability, and Bayes theorem is just very special type of the conditional probability. And let's look at it. So for Bayes theorem, there are two important events, right? One of them is called prior event, corresponding with the prior probability. So it's the initial probability value originated before any additional information is provided. Meaning, let's say you go to FIT, right? We know FIT has a lot of female students. So let's say FIT has 70% of female students and 30% of male students. And that's a prior probability, right? So let's say this is a given condition before any new information is released. And we also have anything after the previous information has been released. If we obtain new information, this is what we call posterior probability, posterior events. Probability value that has been revised using additional information that's later obtained. If we know that, if we have the later information out of 70% of female students let's say 80% of them using Mac, right? 20% of them using Windows. So that will be a different piece of information based on the previous information, right? Previous breakdown is 70% female, 30% male. Now, the second layer is additional information is out of 70% female students, let's say 80% of them using Mac, and then 20% of them using Windows. Right, so 70% female at FIT. Again, this statistics may be off, right? Just randomly make up this question. Female. Just show you how this Bayes theorem will be structured. Male students. Okay, and 80% of 70% female students using Mac, and then 20% of 70% female students using Windows. And this is exactly the kind of structure we're looking at in terms of the Bayes theorem. So this is what we call the prior information, right? This is what we call the information obtained after this. So it's additional information being provided. So we call this posterior probability, prior probability, and posterior probability. And this is how we look at the Bayes theorem in terms of structure. And the formula to calculate the Bayes theorem, the probability of event A, given that event B has subsequently occurred, will be probability of A given that B occurs, probability of A times probability of B given that A occurs, right? And also dividing by probability of A times probability of B given that A occurs, plus probability of A not occurring times probability of B given that A not occurring. So it's like this. So if you draw this, so first layer is 70% female, okay, and male, right? Second layer is Mac or Windows. Okay, same thing for male, right? We're gonna take a look at the male in this. So we know that this is 70%, 30%. And this is 80% and 20%. Even hypothetical speaking, let's say male students for Mac and Windows. Okay, so the Mac will be, let's say 70%, and then Windows 30%. Okay. And what if you want to find out probability that Mac users, given that it's a female, right? Mac users, given that it's a female. So basically you are saying that for all the Mac users, what percentage of them are females, right? So you have male users using Mac, females are using Mac. So basically you're looking at this. Out of all these Mac users, given that it's female, so you do probability of Mac user times probability of female, given that using Mac, right? And the bottom, you know, will be probability of same thing, Mac users times probability of female, given that it's a Mac user, adding probability of Windows users, divided Windows users, given that times probability of female who is using Windows, condition using Windows. Right, so that's basically how you interpret this formula, translating into a actual problem, right? So that's how you handle this problem. Okay. All right, so now let's look at the actual example, right? So let's say in Orange counties, 51% of them are female, 49% of them are male. 51% female are male, and 49% females. And one adult is randomly selected for a survey involving credit card usage. Okay. Find a prior probability that select person is a male. Okay. So that will be, if you look at it, male percentage is 51%, right? So that's what this is about. And then it's later learned that the survey subject was smoking a cigar, and 9.5% of male smoke cigars, and only 1.7% of the female smoke cigars. Now find the probability the subject, the select subjects is male, right? And so basically, you look at the prior information here is 51% males and 49% females. And the secondary information is the information after additional information here is 9.5% males smokes cigars. And that means 9.5% males do not smoke cigar. Okay, so that's breakdown of that. And also for female counterpart, 1.7% of female smoke cigar. And then the remaining percentage will be 98.3% of female does not smoke cigar. Okay, so that's a breakdown based on the additional information. That's how we break down that. So now, using M represent male, M bar, meaning complement event of that will be female, right? So you will look at female will be the complement of male. And then cigar smoker, using C represent cigar smoker, C bar or complement of C bar will be not a cigar smoker. Okay. So using this to represent all these different events. So before the extra information of 10, we know that 51% adults are male, right? So probability of male is 0.51. So probability of female or complement of male will be 0.49. Okay. So you can list those two. All right. And now probability of, so we figure out those two. The probability of cigar smoker given as a male is 9.5% of males smoke cigars, right? So it's 0.095. And if you look at not smoking cigar, right? Probability of non-cigar given as male, we can also write that it will be 0.905. This indicates a probability of males who do not smoke cigar, it's 90.5%, so it's 0.905. And the last expression here is probability of not male, right? Female who smokes cigar. So will be 1.7%, so it's 0.017. And the counter argument will be probability of female, okay, who do not smoke cigar, right? That will be 0.983. Okay, so this is all the, now you can apply the Bayes theorem. Okay, so you do this, male, female, right? smoking cigar, not smoking cigar. Okay, now we just throw it on the numbers. Male, we know it is 0.51. Okay, female is 0.49. All the males who smoke cigar is 0.095. That's probability associated with it. Not smoking cigar with 0.905. Okay, and for female, maybe put it here, it's 0.017, smoking cigar. Not smoking cigar is 0.0983. Guess it's easier to just put it on the side. So this is 0.095, 0.905. Okay. And this is how you use a tree diagram to visualize what's going on here. And eventually, what they want us to find is probability of, let's go back to the question and see what they want. Now find the probability that select subjects male, right? So male smoking cigar, right? Okay. So probability of given that it's male who smokes cigar. Okay. So now you want to take a look at this, smoking cigar. So you want to find out the percentage of the male who smokes cigar, right, out of this. So here, this is that, and this is another group who smokes cigar, right? Given that smoking cigar. So it will be 0.51 times 0.095. Okay, that's one group, male smokers who smoke cigar. And 0.51 times 0.095, okay, plus the other group is the female who smokes cigars, right? So it's 0.49. So you basically want to find out what percentage of the male smokers out of the entire population. And that should be the conditional probability we're looking at. And let's see what that is. So it's 0.59. 0.51 times 0.095 male who smokes cigar divided by 0.01 times 0.095 adding 0.49 times 0.017. And this turned out to be 85.3%. Okay, approximately 0.853. And it's turned into percentage of 85.3%. Okay, and that's how you look at that. So out of all those cigar smokers, right, 85.3% of them are male, meaning the female will be 14.7% over the entire population. Okay. All right. Any question on this? So creating a tree diagram like this will help you, visualize what's going on here, and try to understand what they try to ask you, and then you should be able to quickly get a result. Now, Bayes' theorem generalized. Preceding formula use exactly two categories for event A. So two categories for event A, right? Smoking cigar, we have male and females. That's what we call two categories for event 8. The formula can be extended, include more than two categories. That's also possible. And we just want to make sure, all those multiple events satisfy two important conditions. Events are disjoint, right? Meaning they are independent. They do not overlap each other. And also events must be exhaustive. Means they combine to include all possibilities, meaning it has to include all the possibilities here. So as soon as those two are satisfied, then we apply the Bayes' theorem, even with the more than two possibilities, right? In the previous question, we only have two possibilities, male, female, right? So that's why only two possibilities. But for some cases, You'll see that in a second. Let's take a look at this example one, right? Let's say Dr. Forster remember to take his umbrella with him 80% of the day. Now, another way of saying this is the counter argument is 20% of the time he forget it, right? Forgets 20% of the time. Days. And then it rains on 30% of the days when he remembered to take his umbrella, and rains on 60% of the day when he forget to take his umbrella. And you want to find out probability that he remembers his umbrella when it rains, right? So this is like probability of remember given that it rains. Right, that's what you try to figure out. Now, you probably want to structure a tree diagram really quickly. So here, two scenarios, either he remember or he forget. Remember with the 80% of chance, forget with 20% of chance. When he remembered to bring the umbrella, 30% of the day, it rains. And that means not rain. No rain. No rains. Okay. %70 of chance. Okay. Now when you forget, he rains 60% of the day when he forget to take his umbrella. So rains 60% of the time. And no rains. Will be 40%, right? Will be the complement. Now, if you look at it, you want to see when he remembers to bring his umbrella, it rains, will be the probability out of this. So you're looking at these two groups. Remember, it rains. He remembered to bring umbrella given that it rains. Also, he forget to bring umbrella when it rains. So now, yeah, that should be this. So on top, it should be 80% times 30%. It rains, but he remembers to bring it. It rains, remembers to bring it. Also, it rains, but he forget to bring it. So it's 20% times 60%. Okay. And that becomes the total probability. So here 80% is 0.8 times 0.3, and 0.8 times 0.3, and 0.2 times 0.6. So this is 0.24 over 0.24 adding 0.12. So it's 0.24 over 0.36. This is 2/3 basically. Right? If you want to put in the exact answer, it will be 2/3. So the probability is 2/3. Also, if you want to put in a decimal, it will be 67% approximately. So that indicates the probability that he remembers umbrella when it rains will be 67%. So that's how you will handle the Bayes theorem applying using the tree diagram. Right now, I want you to look at question 2 and try to work it out yourself. And this one, I also have machine X, machine Y, right? So two different machines. Machine X produce 60% of the daily output. Machine Y produce 40% of daily output. And 2% of machine X output is defective. 1.5% of the machine Y's output is defective. One day, an item was inspected at random, found to be defective. And then the manager want to figure out, for this defective item, which machine produces, right? And you want to find out that probability that it was produced by machine X, assuming it's a defective item. So you do probability of defective item for machine X, right? Given that it's a defective item. So the prior information, the first piece of information is defective. Second one, you will find out what's probability that machine X produced a defective item. out of all defective items produced. Okay, I'll give you 5 minutes. Think about this. Draw the tree diagram, and then it will help you a lot. Okay, so let's look at the solution for this. Again, you're gonna produce a tree diagram. We can do it here, right? We have two different kind of machine, right? Machine X, machine Y. And machine X produces some good items, right? Outputs that could be defective. Machine Y, same thing, good items, defective items. We know that 60%, machine X produces 60%, machine Y produces 40%. For good ones, only 5%, 2% defective rate for machine X, 2% here. So it means 98% of them are good items. Okay, for machine Y, defective item is 1.5%. So the good ones will be 98.5%. Okay, so that's a breakdown. Okay, and based on this, we're looking at the X defective, right? So two sources produce defective, machine X and machine Y, here and here. You want to find out percentage produced by machine X. So 60% times 2%, that's defective item produced by machine X with 1.2% of chance. And 60% and 2%, adding the defective item produced by machine Y with the associated probability with 40% times 1.5%. Okay. And just simplify, right? So it's 0.6 times 0.02 over 0.6 times 0.02 plus 0.4 times 0.015. Okay, so this turned out to be 0.012 over 0.012 plus 0.006. And this turned out to be 0.012 over 0.018. And this turned out to be 2/3. So again, 2/3 of chance. When you turn your percentage, will be about 67% of chance. Okay, it will be produced by the machine X. Okay, so that's how you handle this conditional probability in terms of the Bayes theorem, using Bayes theorem. And then quickly, any question on this? Okay, let me just mention the homework assignment one more time. Actually, I do post the homework assignment needed to be completed for chapter 4. You can only work on section 4.1 and 4.2. Let me share the screen with you. So homework assignment 4.1, 4.2, all questions, right? All of them, not our ones, right? So if you open the textbook, and 4.3, 4.4, they do not have a exercise in the back of each section, so that's why I'll omit it. So you do have just to complete the 4.1, 4.2. Okay. And also, if you need more exercise, in terms of probability, you should definitely try the test number 3 review for the final exam. It does have a lot more problems here, right? So I would strongly recommend you work on this before Friday when we go over the review questions. A lot of this question, we talk about, so you should try yourself first before Friday's review section, and it will be very helpful, right, in terms of the preparing for the final exam. Okay, and yeah, if you have some time left, so if you have any question in your project or maybe from a homework assignment, let me know, right? I could talk about it. Okay, we still have about 15, 20 minutes. And in that case, I'll put you guys in the breakout room and you can talk to me on an individual basis if you still have any questions. Okay.